Jain everyone. I am Shruti Jain, Assistant Professor at MC Department, Ajay Kumar Garg Engineering College, Ghaziabad. The topic that I am going to discuss today is the group theory topic, and this topic is covered under the Discrete Mathematics subject. The subject code is BMC 104. This is specially meant for MCA first year students. So let's understand first what a binary operation is. So as the name suggests, binary is anything that has two things with it. So a binary operation on a set is a rule for combining two elements of a set. Like if we talk about plus, when I write A plus B, so this plus over here is a binary operator because it needs two operands to work upon. So similarly, a binary operation, if we are working on a set, it is a rule for combining two elements in a set. So if we come to more into the definition part more precisely, if S is a non-empty set, a binary operation is a mapping from S cross S to S. That means if suppose I have any binary operation, let's take an example of this plus only. So this A is the element of S, this B again is the element of S. This is a binary operation, and the resultant that I will be getting C is also an element of this S. So that means it is on a mapping S cross S, or it could be any set. Here we are taking a single set S on which we are doing the mapping. So S cross S that goes to S. Thus F associates with each ordered pair X and Y of the element of S and element Fxy of S. So this xy is what we are talking to this AB, and this f of xy, the resultant that we are getting, that is this, will be this element C over here. Let's take an example. If we take the operations of addition and multiplication, we know that these are the binary operations because it needs two operands to work upon and it gives you a resultant. So these are the binary operation on the set of integers. Since for all a comma b belonging to z, a plus b, that is the addition of two integers, again is an integer. The multiplication of integers is also an integer. Hence, we say that the operations of addition and multiplication are the binary operations on the set of integers z, or z is the notation for integers. Similarly, we can take it as if we are, that was a set of integers. Now, if we are taking any of the power set or any non-empty set S, in that case, if we talk about the operations of union and intersection, this is the union operation and this is the intersection operation. So, the operations of union and intersection again are the binary operations on the power set of non-empty set S. Because whenever we are doing the union of two sets, we'll get the ordered pair that will belong to the power set of S. Similarly, if we do the intersection of any two sets, so either the ordered pair that we get or a single element that we are getting will also belong to the power set of S for all a comma b, that is the subset of S. A comma b, the condition for a comma b over here is that these should be the subsets of the original set or the non-empty set S that we are taking out over here. Now, we have certain operations like we have discussed about the operation of binary operation. The first one is the unary operation. The unary operation is that goes from set A to set A, or anything like it could be A to B as well. Binary operation where we have a Cartesian product of two sets, will get an ordered pair x comma y over here and will get an element maybe z over here. So x comma y going to z is a binary operation. When we are talking about the ternary operation, we have the three sets combined together. That means the pair that here will be x comma y comma z, which will maybe either going to any of the element of A as P, where we have all these elements are belonging to the set A. Similarly, for n factor or n-ary operation, we have A Cartesian with A multiple number of times, n number of times, and the resultant would be going to A itself. This is known as n-ary operation. So coming to the properties of binary operations, if asterisk is a binary operation, this asterisk could take any of the operator. It could be a union, it could be an intersection, it could be addition, multiplication, or it could be any operator that is given to us in our question. But in general, if asterisk is a binary operation on a set A, then it follows certain properties, these 7 properties: the closure property, associative property, identity property, inverse property, commutative, cancellation, and the distributive property. So let's talk about these properties one by one. The first one is the closure property. The closure property says that if there are 2 elements A comma B which belongs to A, then the binary operation of these two A star B or A asterisk B should also belong to the set A. For example, if we say that we have 2 elements 2 comma 3 over here, and this asterisk is a plus operator that we are talking about, then this A is maybe a set of integers, the positive integers. So plus, that is 2 plus 3, that will get as 5, will also belong to the set of positive integers Z. If this is true, then in that case we say that the closure property holds true. Associative: if the elements A comma B comma C, if we have 3 elements A, B, C that belongs to a set A, then the operation asterisk on A asterisk B asterisk C is equal to A asterisk with B asterisk C. Let's take an example with the plus operator only. If we have 2 plus 3 plus 5, it should always be equal to 2 plus 3 plus 5. So in that case, 2 plus 3 would be 5, 5 plus 5 would give us 10. In this case as well, 5 plus 3 is 8, 8 plus 2 give us 10. So this also holds true. Next, identity element. There exists a unique element E on a set A such that for any element A belonging to A asterisk E is equal to A is equal to E asterisk A. That means an identity element is such that whenever we do the binary operation of it with any element in that particular given set, we'll get that element itself. For example, if we talk about the plus operator, here the identity element is 0. So if I add 0 to any element, I'll get the same element as 5 only, or maybe that same element. So here if I have 5 as an element, if I add 0 to it, so 0 is the identity element if we are talking about the plus operator as a binary operator. Inverse: for every element in a set A, there exists a unique element A dash such that A asterisk with A dash gives us the identity element. That means if we are talking about the plus operator over here, so here what should I add to this so that I get the answer as 0, because E is the identity element that we have just discussed over here in this. So here we'll have minus of A as the inverse of A when we are talking about addition as the binary operation. So for example, if I take 5 added with minus 5 will give us 0. So this would be possible only when we are talking about the set of integers. So here in this case, minus 5 will be the inverse of 5. Commutative: if the elements A comma B A comma B belongs to A, then A asterisk B is equal to B asterisk A. That is simple. For example, if I take 5 plus 6 will be 11, which will be equal to 6 plus 5. Hence, the commutative property also holds true when we are talking about the plus as a binary operator. Cancellation elements, it says that if the elements A, B, C belongs to A, then A asterisk B is equal to A asterisk C, which implies B equals to C. Let's take it for the addition itself. If I say that 5 is A, if this A, let's take this 5 as A. If I do 5 plus 6 is equal to 5 plus 2, in that case, I'll automatically have 6 equal to 2. That means this 5 gets cancelled up. So in that, this is the cancellation property. Distributive: A asterisk B asterisk C, A asterisk B plus C is equal to A asterisk B plus A asterisk C. So this also will hold true when we are talking about the plus operator. Coming to the group theory, we'll start with the first one, that is the algebraic structure, that is a basic structure, which only talks about the closure property holding true for any binary operation given to us. So algebraic structure is a structure where we say that if a set is given to us and if it satisfies a closure property on each and every element of the set, then it is also known as an algebraic structure. When in the algebraic structure we add the associative property to it, it becomes a semigroup. So a semigroup is a group of a set of numbers where the closure property as well as the associative property holds true. When we add the existence of the identity to it, it becomes a monoid. So a monoid has three properties. It satisfies the three properties: the closure, associative and the identity property. Adding the inverse property to it, the monoid, it becomes a group. So group holds four properties: the closure, the associative, the identity and the inverse. The last one, once we add the commutative property to it, it becomes an abelian group. So an abelian group is a group which holds all the type of properties, that is the closure property, the associative property, the identity, the inverse and the commutative property. Let's look at the definition, the formal definitions of each and every one. So algebraic structure, let S be any non-empty set with an operation asterisk. Thus, S is called an algebraic structure with respect to the operation asterisk if it satisfies a closure property, that is A asterisk B belongs to A. So, for examples, we have the set of natural numbers on addition. 2 plus 5 gives us 7, which again belongs to A. Set of integers, minus 2 plus minus 3 gives minus 5, which is again an integer. Z on negative integers, suppose I have Z with minus, suppose I have 2 and I have 2 and 3, 2 minus 3 gives us minus 1, which is again an integer. Hence, it is an algebraic structure. Natural numbers on addition, integers on addition and integers on subtraction are all algebraic structures. Coming to a semigroup, when we add the associative property to the algebraic structure, it becomes a semigroup. So an algebraic structure S with an asterisk as a binary operation, where S is a non-empty set with an operation asterisk, then S is called a semigroup with respect to asterisk if it satisfies the closure and the associative property. The associative property says A asterisk B asterisk C is equal to A asterisk B asterisk C. So if we take an example of natural numbers on addition, again 2 plus 3 plus 5 will give us 10 again, and here 2 plus 3 plus 5, that is 2 plus 8 will give us 10. Hence, natural numbers on addition is a semigroup. Similarly, the integers on addition is also a semigroup. If we take the same integers or maybe the negative integers, we'll get the semigroup. Monoid, make it a monoid. So here if we have the addition of numbers, in that case E, the identity becomes 0. Anything added to 0 gives us the same number. So identity element in the addition as the operation, binary operation becomes 0 becomes the identity for the addition operation. Similarly, 1 becomes the identity for the multiplication operation, because when I multiply 1 by any number, I get the same number. So this is the multiplicative identity. We call this as multiplicative identity. Whenever we have multiplication as the binary operation, and if I add 0, so this becomes the additive identity. When we have plus as the binary operator. So there exists a unique element E in a set A such that for any element A belonging to A asterisk E, so in case of multiplication we have 1 and in case of addition we have 0 as the identity, then E is called the identity element for the operation asterisk. Coming to group, when we have the addition of the inverse property or the inverse of an element, in that case it becomes a group. So an algebraic structure G star asterisk, where G is a non-empty set and asterisk is a binary operation, it is said to be a group if the operation satisfies the closure property, the associative identity and the inverse of an element. So if I talk about the additive inverse, in that case we just saw that 5 when added to minus 5 gives us 0, that is the identity, because the inverse of an element says A along with its inverse when does on a binary operation we gets an identity, and the identity element over here is 0. So 5 plus minus 5 gives us 0. This is the additive inverse. We call this as additive inverse. Similarly, when we are talking about the multiplication, when I do 5 multiplied by 1 by 5, I get 1 because 1 is the identity element of the multiplication as the binary operation. So in that case, I will have 5 multiplied by 1 by 5 gives us 1 because 5 cancels out and I get 1 over here. So 5 multiplied by 1 by 5 gives us 1 here. This 1 by 5 becomes the multiplicative inverse. So in that case, on a set of real numbers, we say that on a set of real numbers, multiplication forms a group. Similarly, on the set of integers, addition forms a group. Abelian group, when we add the last property, that is the commutative property to the groups, we get it as an abelian group. So an algebraic structure G asterisk, where G is a non-empty set and asterisk is a binary operation, it is said to be an abelian group if the operation asterisk satisfies the closure, associative, identity, inverse and the commutative property. So the commutative property says A asterisk B is equal to B asterisk A. This is very simple. When we say that 6 plus 5 is equal to 11, which is equal to 5 plus 6 in case of addition, 6 into 5 is 30, which is equal to 5 into 6 in case when we consider the multiplication as the binary operation. So this is what we have just discussed. Let's take it, let's understand it one by one. So when we are talking about this is the algebraic structure. This is a monoid. This is the semigroup. We'll write it down over here. This is algebraic structure. This is semigroup that we are talking about. This is a monoid. This is a group. And this is the abelian group. So when we talk about the natural numbers on addition, where we have the closure property only holding true, so it is an algebraic structure. It is a semigroup because it satisfies the semigroup. When we talk about the identity element on addition is 0, but 0 is not this. 0 is not a natural number and hence it is not a monoid, and since it is not a monoid, the rest of the things does not follow. Similarly, if we talk about the natural numbers on subtraction, if I take two natural numbers 2, 3, so in that case 2 minus 3 gives minus 1. It is not an algebraic structure and hence nothing follows. Natural numbers on, so till the identity we have its existence because 1 is the identity element, because 1 is the identity element of natural numbers, but as we have seen that the additive multiplicative inverse of 5 would be 1 by 5, which is not a natural number and hence it is not a group because the inverse does not exist. For division, it is not true because if I take 2, 3 as the numbers, then 2 upon 3 does not satisfies it does not belong to the natural numbers. Similarly, set of integers on addition. The set of integers on addition will satisfy all the properties, and hence it is the abelian group. The set of negative numbers, it is an algebraic structure. Again, for a semi-group, it needs to be satisfying the associative property. The associative property does not hold true, and hence it is not a semi-group. For multiplication, again integers, the inverse does not exist. For division, nothing holds true. When we come to the set of real numbers on addition, the set of real numbers on addition, it holds true for all the properties. For negative numbers, it does not hold true, and hence, as we have just seen the example over here, so this does not hold true, and hence it is not an algebraic structure itself. For multiplication, again the inverse does not exist in the real numbers. For division, it does not hold true for any of them. For the exponents, we have this, and for rest of the things, again for the whole numbers and the rational numbers, there are some of the things which holds true and which does not hold true. So this covers up the basics of the group theory, the abelian group, where we have seen that an abelian group is a outermost group or the major group which satisfies all the properties, that is a closure, associative, identity, inverse and the commutative property. That's all for today.